Hello everybody and welcome to this GCSE Chemistry video about organic chemistry. Specifically, we're going to be looking at crude oil and how we refine it ready for it to be used as fuels and also as feedstocks in the petrochemical industry. As you will know from other walkthrough videos that I've done, I will talk out loud about my thoughts behind the questions, and then when I'm writing in green, that will be the answers that are going to get you the marks. So blue for thoughts and green for marks. What I recommend you do is that you pause the screen when we first see the question, and then you can have a go at it before I go through the answers, and then you can see how you've done by watching what I do. This first question is about a chemical reaction that takes place in an oil refinery. And as you can see from the question, we've got compound X on the left-hand side, and that changes into, there's an arrow to show the change, changes into compound Y and compound Z. And then we're told that X, Y, and Z are all examples of which type of compound? Well, what you can see from the diagram is that there are atoms of H, which is hydrogen, and atoms of C, which is carbon, and these compounds, which only contain hydrogen and carbon, are known as hydrocarbons, and so they are only containing hydrogen and carbon. And then the question asks us to delve more deeply into the actual reaction, and then it says what type of reaction is taking place. Well, we've got on the left hand side we've got a large hydrocarbon, and actually that is an alkane hydrocarbon, and we can tell that this is an alkane because there are only single bonds between the carbon atom. And then on the right hand side in the products we've got a smaller alkane than before, and we've also made this molecule compound Y, which is an alkene. And alkenes have got double bonds between their carbon atoms like this here. So alkanes only have single bonds between the carbon atoms, and an alkene has got a double bond. And so the type of reaction that takes a large hydrocarbon and breaks it into smaller alkanes and an alkene is cracking, although you could also call it a thermal decomposition reaction. Either would be absolutely fine. You do not need to say both. And then the question moves on to saying what are uses for these two compounds? Well, alkenes, because of that double bond, they're really reactive, and that can be used to make polymers. So don't just say polymers, but it's for making polymers. Specifically, if you really wanted to show off, that alkene is called ethene, and so what you would actually make is you would make polyethene. But you wouldn't need to say that to get that mark. And then compound Z is an alkane. Those small alkanes are best used as fuels because they're good and flammable. This next question begins by looking at another aspect of oil refining, and that's to do with fractional distillation, and we can see it spelt out down there. The very first part of the question asks us to work out what the formula is of a particular hydrocarbon that has got 34 hydrogen atoms in it. Now, we're told it's an alkane, and remember they only have single bonds, and the general formula for an alkane is CnH2n add 2. And so for this question we actually have to work backwards. If H is 34, then what we must have done to work out the carbons is we must have added 2 on to make 34. So taking 2 off would give us 32. And then we had to double the number of carbon atoms to get 32 in the first place. So working backwards to the number of carbon atoms that must be in it, we need to halve it. And what we get there is 16. So C16H34 is our final answer, which is the second box. And then we dive into the fractional distillation process itself. And in the process, you can see what's happening here is that we've got crude oil entering the fractionating column on the left-hand side at the bottom. And then at that point, heat is applied. And what that does is it turns liquid crude oil into gas crude oil. And so what happens is the vapours are produced in the furnace on the left-hand side. So the heat is evaporating the oil or the hydrocarbon, or it's vaporized. And then what happens is the crude oil then moves into the main part of the column. So this whole thing from top to bottom is called the fractionating column. And what's the characteristic about that is the column is hottest at the bottom and it's coldest at the top. And so what happens is, as the crude oil enters the fractionating column, it gradually cools down. And so the vapours rise up through the column, and once it gets cold enough, the vapours will condense and turn back into a liquid. And that happens at different points depending on how long that hydrocarbon is. And the larger hydrocarbons condense down at the bottom, and the shorter hydrocarbons condense towards the top. And in fact, some really, really long hydrocarbons actually don't even vaporize at all, and they dribble straight back out of the bottom of the column as a liquid. And additionally, some hydrocarbons are so small that they never condense, and they go straight out of the top of the column as a gas. And so what we need to say to secure the 4 marks to describe the process is we heat the oil to vaporize it, and then the vapours rise up the column and condense, and they condense at different boiling points depending on the length of the hydrocarbon. And we need to make sure we've woven into our answer that the temperature decreases as we rise up the column. This next question is talking about the use of that crude oil as a fuel, and it asks you to compare the use of crude oil fuels to fuels derived from plants, so for biofuels. And so we're focusing in particular on the environmental impact of these fuels. So what they're going to be asking you about the plants is they want you to be thinking about carbon neutral, which is one of the huge pluses of biofuels, and also crude oil. First thought is that it is a finite resource, which means it is non-renewable. And so that means that we've got a starting point for how to approach this problem. Now, the first thing that I would say is actually burning both of them as fuels does release carbon dioxide during that combustion, and the carbon dioxide emissions will contribute to global warming. And so that's the first key point here. And when we're answering this question, we don't need to include tons and tons of detail because it's only 4 marks. And so what the mark scheme will say is that they will want 2 or 3 maximum strongly linked supported arguments. And when they say the word evaluate, what that means is somewhere along the lines you need to make a conclusion. And I actually recommend that you make your conclusion first, which is why I left that bit of space for it, because that will encourage you to remember it, and so, or help you to not forget it. So start with your conclusion and then weave your answers, your facts, in support of that, allow that to follow afterwards. And so we've already said that carbon dioxide is released as fuels, and that contributes to global warming. So we can then move on to go into some of our other details. So we can say that fuels from plants are carbon neutral, and what that means is they take in CO2 during photosynthesis as they grow, and they release the exact same amount when you burn them in combustion. Whereas burning fossil fuels can not be counteracted because they take millions and millions of years for the fossil fuels to actually form. We can then move into some other problems of crude oil, because crude oil can release sulfur dioxide when that burns, because there's sometimes sulfur in the crude oil, and sulfur dioxide can then cause acid rain. So each of these answers is sort of coming in a pair, which means that we are linking our first point to our judgment by developing it and explaining why it is important. We should probably consider some negative points about the plants, because there is probably one big downside, and that is when you are using biofuels, they require a large area of land to grow the crops. And what that means is it's called displacing the food crops. It means it's taking up the space for the food crops to grow in, and what that ends up doing is making the food crops more expensive to produce, or maybe there just might be fewer food crops produced, but certainly the food crops that are produced are likely to become more expensive in the process. So there are other things that you could say. You could talk about destroying habitats to grow plants, or you could talk about actually going back to some good things of the plants. You can actually recycle cooking oil, so vegetable oil or sunflower oil can be recycled and then burnt. So that's reducing waste, and so there's some other positives there. But just to finish off, we need to make, I would say, 2 clear points that are then backed up by evidence to secure that 4 marks. But don't forget the conclusion. And then the next question is a bit of a leap forward into polymers, which you can make from alkenes. And what they want you to do here is look at a pie chart. So you don't need to memorize any of this data, but they ask you to look at a pie chart and work out the percentage of polymer used in packaging. And packaging is this big area here. And so we should already have an idea, have a reasonableness check, it's called. And so this is nearly half of our pie chart. So we're thinking maybe it's going to be about half before we start. We've been told there's 45 megatons of polymer used, and so what we need to do is we need to add up these 4 values from the pie chart, and when we do that, we find out that the answer comes to 27 megatons. And so what that means is that the packaging must be the difference between those two. And so 45 take away 27 gives us 18. And so there are 18 megatons of packaging produced, and they've asked us for that as a percentage. So if the total is 45, whenever you're doing a percentage, the percentage is the thing that you're wanting to find out, which is 18, divided by the total, which is 45, and then to turn it into a percentage, we need to multiply that by 100, which, when you put that into your calculator, gives us 40%. And so that was a 2-mark question. If you'd say messed up earlier on and you'd not quite got the right number of megatons, but then you'd maybe carried on and you'd got the percentage correct, that's how you could get 1 mark instead of 2. The question then moves on to take a look at polymerization of ethene. And ethene is an alkene, and we can see that it is a hydrocarbon which has got the formula C2H4. So we know it's an alkene, so the first thing I suggest you do when you've been asked to draw the displayed formula of an alkene is you draw the double bond with the equal sign between those 2 carbon atoms. And the displayed formula, that means show all of the bonds between all of the atoms. So this is what's called the molecular formula, C2H4, but the displayed formula, you show all of the bonds. And so we've got 4 hydrogen atoms to put in, and so we need to put 2 onto each carbon atom, because the carbon atoms need 4 bonds each in total, and that's what we've achieved with this structure here. And then the question moves on to ask us about polymerization as a process. Now, polymerization is where you take many small molecules, and these small molecules are called monomers. And these monomers take their name in 2 parts. So first of all, mono means one, and mer means part. And so these are single small molecules, and what happens is they join together. We don't need most of this space, so I'm going to leave a line. So they join together and they make a polymer. And you could, instead of saying make a polymer, you could describe the polymer, which is a large molecule. So the small molecules join together to make one large molecule, so many small molecules. And then the question finishes by taking a look at the structure of a polymer. And the question says that we've got a polymer, polypropene. Now, the names of polymers are really easy. They sound complicated, but they're really easy. So poly is put in front of the name of the monomer. And so the monomer was propene, and we've got its structure shown here. And we make the polymer polypropene. Butene would make the polymer polybutene. It is just as simple as putting poly in front of the polymer's name. Now we're being asked which structure represents polypropene. And so what we need to be looking at here is we need to be looking at seeing whether the structure that I've put inside the brackets here is replicated inside these brackets. Now, it won't be replicated precisely, because what happens in polymerization is the double bond breaks and it becomes only a single bond, and the chains grow from either side of those two carbon atoms that did have the double bond. So what I've just done now, that's what we're looking for inside the brackets. And so the first one looks pretty good. I think the first one is going to be the answer, so I'm going to put a tick there, but we'll just check the others just in case. And the reason that I think that's good is we've got 2 hydrogen atoms on the first carbon, tick, that's what we've got, and we've got a hydrogen and a CH3 on the second carbon, so that's all good. The second diagram that we've been given is no good because of that CH3 there. We don't see that up in the monomer that we've been shown, so that's no good. And look, we've got it again there, so that's definitely wrong. And we've got it again there, actually, so we can see that there's clearly those 3 aren't right for the reason of the CH3 in the bottom left-hand corner each time. And in fact, as we work from left to right, each one has an extra CH3 group attached, and that's what makes these wrong, because you can see that our original monomer, propene, only has the one CH3 group in the bottom right-hand corner to match this structure here. This final question starts by looking at some of the properties of the different hydrocarbon fractions that you can get as a result of fractional distillation. And so we're presented with a table here where we've got 4 of the different fractions named, and then we've got an example of an alkane in each of those 4 fractions, and then we're presented with the boiling point of the alkane from within that fraction. And so we're asked about the boiling point twice, so let's just clarify what boiling point is before we start. And so if we have a simple number line with temperature on that line, the boiling point, I'm just going to pick a point here, and I'm just going to write BPT for boiling point. At temperatures above that boiling point, this substance, whatever it is, will be a gas. At temperatures lower than the boiling point, that substance will be a liquid. And so we've been asked to suggest the lowest temperature that this crude oil mixture needs to be heated in order to vaporize all of these fractions. So we want all of them to be in the gas state. And so looking at each boiling point in turn, the boiling point of petroleum is -42, so that's a really, really cold temperature. And then the gasoline or the octane is a higher boiling point, dodecane even higher, and ecosane is even higher still. And so that is the highest boiling point of all 4 of them. And so in order to vaporize all 4 of them, we would need to heat it to 344 or above. So in fact, there would be a number of acceptable answers for this question. So anything from 344 to, say, up to 350 degrees C. So we've got a range of possible answers. And so once you hit 344, this number on the side, we would then have evaporated all 4 of those fractions. The question then goes on to ask us a specific question about the dodecane fraction, and so that boils at 216 degrees Celsius. And so at what temperature will dodecane condense to a liquid? That really is trying to catch you out, I think, this question, because the answer is 216, because if you are warming up your chemical, the boiling point is the temperature it changes from a liquid into a gas. But if you're cooling that temperature down, it will turn from a gas into a liquid at that same boiling point. So if you like, that's the tipping point between liquid and gas. It's the temperature it both condenses and evaporates at, depending on whether you're warming up or cooling down. This next question is a bit of a test to see if you remembered what we discussed earlier, because it says, describe what happens in the fractionating column that allows these fractions to be collected. And hopefully you remember this, that when the vapours rise up the column, they cool down. This causes the vapours to condense, but they condense at different temperatures depending on their boiling point. And that boiling point depends on the number of carbon atoms in each of the fractions. And ecosane has actually got 20 carbon atoms, which is why it's got the greatest boiling point. And then dodecane has got 12 carbon atoms, octane has got 8, and propane has got 3, which is why it has the lowest boiling point out of all 4. It evaporates the most easily. And then the final part of this question is about combustion, and specifically we've been asked to balance these equations for the combustion of propane in air. And if you don't like balancing equations, I've dedicated an entire video to that, so I suggest you check that out if you find it really, really difficult. But I'm going to walk you through these questions, and my advice here is to start with the easiest element first. What I mean by that is don't pick oxygen as your first element to balance, because oxygen in both equations appears in 3 different substances and it appears in 2 compounds on the right hand side. So leave that until the end. And the goal of balancing equations is that the atoms on the left-hand side in the reactants need to be equal to the atoms on the right-hand side in terms of how many of each element you've got. And so what we need to do is we need to look at our left-hand side, because that's the place where we've got the greatest detail. We've got propane, which we know is C3H8. Here is its formula. And then we've got a 2 in front of it already, so they've begun the balancing for us. And so in terms of carbon atoms, since we've got 2 in front of the propane, we've actually got 6 carbon atoms in total, and we've actually got 16 hydrogen atoms on the left-hand side. So that's really, really helpful. Then when we move over onto the right-hand side, we need to have 6 carbon atoms as well. And we've got, right now, we've only got the 1. And so these numbers that are in the equations are multipliers. So we put that 6 in front of the CO2, and what that does is that multiplies everything that comes after by 6. So we've now got 6 lots of that 1 carbon, which of course is 6. We've now got 6 lots of the 2 oxygen, which is 12 oxygen on the right-hand side in that particular molecule. And then when we look at the hydrogen, we've got 16 hydrogen in the reactants. We need to have 16 hydrogen over here in the products, and right now we only have 2. And so you multiply 2 by 8 in order to get 16 in the water molecule. So 8 lots of 2 is 16. So that's the water molecules balanced as well. But as well as having 16 hydrogen, we've got 8 lots of that 1 oxygen, and 8 times by 1 is of course 8. And so we've got 12 oxygen in the 6 CO2, and we've got 8 oxygen in the H2O, and so 8 and 12 add together to make 20 oxygen on the right hand side. And so on the left hand side we've currently only got 2, and so we need to multiply 2 by 10, and that gives us a total of 20 on the left hand side. So that equation is now balanced. Speeding on to the second one, and we'll do that one faster, we've still got the same number of carbon atoms on the left-hand side. 2 times by 3 is still 6, and 2 times by 8 is still 16 for the hydrogen atoms. And what that means is the numbers on the right-hand side of the products are going to be the same 2 numbers as before, 6 and 8, for the exact same reasons. But because the first of the 2 products is carbon monoxide, when we multiply that 6 by the 1 for the 1 oxygen, that of course only gives us 6 oxygen in carbon monoxide to go with the 8 that is still in H2O. And then 6 added together with that 8 gives us a total of 14 oxygen on the right hand side, which means in order to get 14 oxygen on the left hand side, we need 7, because 7 multiplied by 2 is 14. And then the very, very final question of all says, how has this happened? How have we got different chemical reactions taking place? And the answer is all to do with the CO2 in the first equation and the CO in the second one. And you can see actually the follow-up reason that in the first equation we've got 10 oxygen molecules, and then in the second one we've only got 7. So what we need to say is that the first reaction is complete combustion, because there's an excess, there's plenty of oxygen, it's burnt properly. And then in the second reaction, we've got incomplete combustion taking place because there isn't enough oxygen and we're only making carbon monoxide in the products. Okay, that's the end of this question walkthrough. I hope it was useful. I'll see you again next time.